Greetings everyone, welcome back. In the previous video, we have learned about the pedigree diagram. In this video, we will learn about sex-linked diseases. This video will be broken down into two parts. The first part, we will learn 3 case studies, and the second part, we will discuss about your past year papers. Now, specifically what we will learn about the sex-linked diseases are, we will learn about color blindness, hemophilia, and also sickle cell anemia. And I want you to pay special attention to sickle cell anemia. Now, we have already learned that genes comes in homolog series and genes are carried by X and Y chromosomes. Okay, so X and Y chromosomes exist in the location 23. So at chromosome homolog 23, you will find the sex chromosomes or the chromosomes that will determine gender. Case study 1, color blindness. Color blindness and the other two diseases are sex-linked syndromes. These are basically genetic defects. Now, how does genetic defects occur in these case studies? Now, we have to establish the fact that genes are always in homologous pair, and for sex-linked syndromes, these defects will occur in chromosome 23, which determines gender. So, if you look at most genetic defects, the defects always occur in chromosome X and Y. Okay, if you look at the diagram here, the genetic codes are marked with fluorescent green, and you will see X and Y. Now, if you look at X is significantly longer than Y. Okay, X is significantly longer than Y. This is the same reason why males are always the afflicted. So, if you have two identical pairs, there are chances of the female individual to be a carrier, to be the afflicted or normal. That is why it is sex-linked. Now, on chromosome Y, you'll realize that the genes are short. Some of the genes present in X is not present in Y. So, sometimes the Y chromosome will carry most of these defects. In order to understand that the sex-linked diseases, we must establish few facts. Okay. Now, we already established the fact that chromosome X and X are female, X and Y are males. Now, gene comes in pairs, and some genes are linked to gender, which is chromosome 23. Now, there are genes which are dominant, genes which are recessive, and genes which are co-dominant. So, in the case studies, we will see there are some genes which are recessive and some genes which are co-dominant. This one we will discuss in sickle cell anemia, co-dominant genes. In order to do these questions and these examples more effectively, there are few rules to remember. That is, the first one, the capital letters are always bigger than the lowercase. It takes first order. You have to write the genes and the codes in alphabetical order. Do not change given coding unless it is specified in the question. Okay, let's deduce case study 1, color blindness. Now, for color blindness, the male is either normal or colorblind. I represent it as CB. Now, for double X is female and XY is males. So, the sex-linked diseases are normally recessive, and the genes are always represented as lower cases. Okay, lower case. So, here we have 5 distinct genotypes and phenotypes. Later, I'll summarize it. So you will see that I have capital B and lowercase b. So these genes will play a huge role later in determining the phenotype of the individual. Okay, let's look at the first genotype and phenotype. The first genotype is X and X, so it is a female, okay, female individual. But the gene carries a capital B, okay, a capital B. But sex-linked diseases are recessive, but it must contain lowercase. So X and X, this one is female with homozygous genes. Okay, homozygous in the sense where it has capital B and capital B. Okay, capital B and capital B. So this person is normal. Okay, normal, because we don't have the lowercase b. So the next one also X and X. The difference is the person here has a capital B and a lowercase b. So X and X is female, but this time it is heterozygous gene. Heterozygous gene because of the small changes in the capital B and lowercase b. So we put it as heterozygous genes. But if it carries the lowercase b here, okay, this person must be a carrier, because the lowercase b can be transmitted to the males. Okay, now the third case here is both also you have double X. Okay, both are double X, so this is a female, but the female genes here carry the lowercase b, and this time it is homozygous genes because it carries the same genes, the same chromosome, but this person is afflicted. That means this person has color blindness even though it is a female individual. The fourth one, XY, males. Okay, male, it doesn't carry any lowercase. Okay, any lowercase, so this is male with heterozygous gene. Okay, you might be confused now why I put heterozygous for double X here and XY also put heterozygous genes. The reason is, you see X and Y, the main genes are different. Okay, this one is in the sense where the color blindness gene is stacked on. One you have capital B, one you have lowercase b. So this person, even though it's heterozygous, the person is carrying the capital B and this person is normal. Okay, now the last one is X and Y, so we know this is male. Okay, the difference is you'll see that the X chromosome here carries a lowercase b. That is the reason it is known as sex-linked diseases. Okay, because in the ovum there will be always X chromosome. Okay, the one that will determine the gender of a child is a sperm. The sperm either will contain Y chromosome or X chromosome. Okay, Y chromosome or X chromosome. So if the woman is a carrier, she's already carrying the lowercase b. Okay, the lowercase b, and it will be inherited by the male. So this male is with also heterozygous. Okay, but this person carries color blindness. Now from the genotype itself, we can actually make an assumption that color blindness is a recessive gene. Okay, color blindness is a recessive gene. Now this is just to deduce. We will use the 1314 method and also the Punnett square to actually show the probability. Okay, if you have no idea on how to do the 1314 method, I suggest you to go to the previous video, chapter 17, pedigree diagram. I'll teach you in depth on how to use the 1314 method. From the information I've given you just now with the 5 distinct genotypes and phenotypes of an individual, let's do the test cross. Okay, we have set up a test cross. We'll use 1314 method and also the Punnett square. For 1314 method, let's look the cross between a normal man, okay, represented by X with a capital B and Y, the carrier woman, okay, carrier woman with the X with a capital B and X with a lowercase b. So I've set up the test cross for 1314 method as such. So we will do the cross shortly. Okay, for the 1314 method, I have written the genotype. Okay, and then I split the genotype into its individual forms. Okay, I have XB, Y, XB with a capital B and X with a lowercase b. Now I'm going to do a cross for F1 generation parents, then F1 generation the child. So let's do the 1 3 1 4 method. So you use a ruler. Okay, 1 3, then 1 4. Okay, 1 3 1 4. So this is X and X. I know I have capital B here, another X with a capital B. This is for 1 3 1 1 3. Now for 1 4 I have X with a capital B, X with a lowercase b. Okay, now I'll do for 2 3, 2 3 and 2 4. Okay, now follow alphabetical order. The X have to come first, X with a capital B, then Y, then I have X with the lowercase b. X have to come first and then Y. Okay, now let's look at the phenotype of F1 generation. XB with the capital ones, both are capital X and B. So this is normal female. Okay, the next one I have both X, but one has a capital B and lowercase b. So this is a carrier female. Now look at the male one here. I have X and Y. I followed alphabetical order. This is normal. Okay, because this is a capital B. This is normal male. So likewise this side I have X with a lowercase b and Y. So this is a colorblind male. Okay, now let's look at the genotype ratio. Genotype ratio. The genotype ratio here is 1 to 1 to 1 to 1. The reason is because the genotypes here are 4 different genotypes, 4 distinct genotypes. You have normal female, carrier female, normal male and colorblind male. So the phenotype ratio is also 1 to 1 to 1 to 1. So in this cross, this couple has a 25% chance of getting a child with these phenotypes. Okay, 25% chance of getting these phenotypes. This phenotype will actually, this cross will actually for each time the person has a child. Okay, so each time a person has a child, the couple will have 25% chance of getting these genotypes. Okay, so that's why sometimes a couple, when they get married and they have children, okay, some children consecutively, the first one will be colorblind, second one will be blind, third one will be colorblind. This is because of the probability, 25% chance of getting colorblind. Just now we have used the 1 3 1 4 method, and let's use the more conventional method, the Punnett square. This time we'll do the crosses in between a colorblind man and carrier woman. A colorblind man will carry the genotype of X with a lowercase b and Y, and a carrier woman will have X with a capital B and a lowercase b. Okay, a capital B and lowercase b. So I split the genotypes and gametes as such, like this. Okay, so I will draw a 2 by 2 square, and I'll list down the genotypes. Okay, on my left hand side I will list down the male, and the top I'll put the female. So how do we go about this Punnett square? So XB and XB. So what do I write is, follow alphabetical order even though it's the gene X, B, X with a lowercase b. Now let's do for the bottom column, the bottom one. So XB, you follow alphabetical order and Y. Now let's do for the second one. Okay, the second one. I have X with the lowercase b, X again with the lowercase b. Okay, now I'll do it for the ones down here. X with the lowercase b and Y. So what is the genotype of my F1 generation? So the first box here, X, B and X, B like this. Okay. The second one, X, B and X, B here. The third one and the fourth one. Okay, now look at the genotype ratio. Now to do the genotype ratio, you have to look at the distinct genes. Are there any repetition in the genes? So we have this one, the first one. Okay, observe. Second one, the third one and the fourth one. Now since there's no any repetitions in the genes, so I will use my genotype ratio as 1 to ratio of 1 to ratio of 1 and ratio of 1. My phenotype is also 1 to 1 to 1 to 1. So my probability is still 25%. Now to deduce what is the genotype and phenotype, double X means female. I have lowercase b here, so this is a carrier, female carrier. Now I have 2X, which is also the female, both lowercase b, so this is a afflicted person. That means this person, female, has color blindness. Okay, look at this X and Y. This is male. You don't have any other genes except for the capital B, so this male is normal. And the final one is you have X and Y, still male, but this person is carrying the lowercase b, which is color blindness. Okay, so this is male normal, male color blindness. Case study 2, hemophilia. Hemophilia is caused by lack of blood clotting factors, and even the slightest injury will cause profuse bleeding. Same as color blindness, it has 5 distinct genotypes and phenotypes. What you have to know is hemophilia is also a sex-linked disease, so it is a recessive gene. So I represent hemophilia with a capital H. So let's look at the hemophilia genotypes and phenotypes. So XY is males. Okay, is male, but you see the H here, capital H, you don't have a lowercase h, so this male is normal. Okay, now I have X and Y, I have a lowercase h, so this is also male. Now if you have recessive gene and it's only one here, that means you are going to become afflicted. So I represent hemophilia as HM here. Okay, now if I have both X, okay, both X, and I don't have any lowercase h here, this is female. This is female, normal. Now this is also female because of the double X, and I have one capital H and one lowercase h here. Remember, lowercase h is recessive. Lowercase h is recessive. So this is also female, but this is a carrier. Okay, carrier. Now, if this is double X, then it's female. But the difference here is it now has 2 lowercase h. This gene has 2 lowercase h here. So this person, even though is a female, they will get hemophilia. Okay. Now from the genotype, we can establish that hemophilia is a recessive gene. Recessive gene. From the 5 different genotypes and phenotypes which we have discussed before this, we will try to do a test cross. The first method that we'll use is the 1314 method. Okay, so what I have done is I take a normal male. I've taken a normal male, and then I have a hemophiliac female. Okay, a person who have hemophilia is known as a hemophilia. So once getting this set up, okay, I write down their genotypes, and then I split the genotypes into the distinct gametes. So I have X with a capital H, Y, X with a lowercase h, X with a lowercase h. Now what we'll do next is the test cross. First we'll do 1, 3, then we'll do 1, 4. Okay, now what is the genotype for this? The first one, we have capital H here, we have lowercase h here, both are X, so I write down as X, H, X with the lowercase h. So this is 1, 3. Now 1, 4, I have also both X, but one with a capital H, one with a lowercase h. Okay, now the next one is 2, 3 and 2, 4. Okay, now let's look at it. Follow the alphabetical order. X comes first, then Y, I have with the lowercase h here, then X, H and Y. Okay. Now the F1 generation genotype would be X, H, the first one, second one, the third one, and the fourth one. Okay, now let's look at the phenotype. Let's discuss the phenotype. This is both X, so it's female, and it has one lowercase h here, so it is a carrier. So female carrier, the first one. Second one, it's almost similar. Okay, it is similar, so it's also female carrier. Now XY means it's male. Okay, male, so X, H here, because the lowercase, this is hemophiliac male, and this is also the same, hemophiliac, because of the XH here, hemophiliac male. Okay, now let's look at the genotype ratio. Okay, genotype ratio. We'll see that both are XH with the same capital and lowercase, so we can tell the genotype is 1. This is also the similar genotype. This is also 1 to 1. So the phenotype ratio is also 1 to 1. In this case, in this test cross, the probability of the child to be hemophiliac is 50%. Okay, 50% between a normal male and hemophiliac female. That means the chances are quite high. Let's look at a Punnett square. This time I'm using a hemophiliac male and normal female. The hemophiliac male is represented by X with a lowercase h and Y, and normal female with X with a capital H, X with a capital H. I've drawn a 2 by 2 square here, and I've listed down the gametes for the female, which is on the top, and on the left is the male gametes. So as usual, I'll do the cross X and this X. Since this H here is a capital H, I put this first, then the one with the lowercase, the one and the below, X with a capital H and Y, the next column here, X with a capital H, X with the lowercase h, and X with a capital H and Y here. Okay, now the genotype of the first generation, F1 generation, would be from the top, X with a capital H, X with a lowercase h. The second one here is X, capital H and Y. The third one, X, capital H, X, lower h, X, capital H and Y. Okay, now as for the phenotype, XX is female, and because of the lowercase h here, this is a female carrier. Okay, X and Y, there's no any lowercase, this is male, normal. X with a capital H, you have a lowercase here, so this is also a female carrier. Okay, and now I have X with a capital H and Y, so I have a male which is normal. So my genotype ratio, look at the genotype ratio, are female carriers which has the same genes. Okay, so I have to put one here, one here, one here, and one here. Now since this is the same genes, so I can write it as such 2, and this male normal is also 2, but now I want to simplify it to the simplest factor, so I will write it as 1, 2, 1. Okay, 1 to 1. Now the phenotype ratio is also the same because I have 2 male normal, 2 female carriers, so it's also 1 to 1. So what is my percentage now? For hemophilic man and normal female, the chances of the child to be carrier, the female to be carrier, is 100%. For the male to be normal is also 100%. Okay, so there's 50-50 chance to be male or female, but 100% chance for the female to be carriers and the male to be normal. Case study 3, sickle cell anemia. You'll see sickle cell anemia again in chapter 18. Why we are doing this in chapter 17? Because it involves the pedigree diagram. So what is it anyway? Now red blood cell is normally biconcave in shape. Okay, but in sickle cell anemia, the red blood cell is sickle shaped. Okay, sickle shaped. Now I've drawn for you the normal red blood cell and also the sickle cell anemia which is afflicted. So in normal ones, it is biconcave in shape. It looks like almost like a donut. Okay, albeit the hole in the middle part of the normal red blood cell is very thin, so it looks like a hole. For sickle cell anemia, it's not like that. It looks exactly like a sickle. Now just like in case study 1 and 2, sickle cell anemia is manifested by recessive gene. The difference here is sickle cell anemia doesn't choose the gender. Okay, it can afflict both male and female. It can afflict male and female. So when we do our Punnett square later, you'll see that I won't write the genders, but I only write the genes. So what does sickle cell anemia does? Sickle cell anemia always cause excessive fatigue or weakness. The joints will be aching, okay, aching joints, and poor circulation. Okay, poor circulation. Now this might seem a little bit biased, but according to the WHO, an individual of African descent is much more prone to sickle cell anemia. Now here's the thing that you have to take note, because this is in your past year questions which we will discuss later. Okay, the second part of this video. So the carriers of sickle cell anemia, that means the carrier genes, are immune to malaria and show a symptom of anemia. Okay, so carriers are immune to malaria and show symptoms of anemia. So they can be immune to malaria, but at the same time they are anemic. To reduce this sickle cell anemia, I'll rather use the Punnett square instead of the 1314 method, because Sickle cell anemia doesn't distinguish gender. It afflicts both male and female. Okay, so this is called dihybrid inheritance. It also involves codominance. Okay, codominance. Now, the only way you're going to know the gender of the person is by looking at the keys which are given. Okay, you will not get to distinguish the F1 generation, but you will know the parent. Okay, you will know the parent. So the keys to the alleles which are given are HBA, capital A, which is normal. HBS, the lowercase one, is sickle cell anemia. Okay, sickle cell anemia. Here I've given you the cross. We'll be doing the cross test for female carrier and also male sickle cell anemia, the afflicted. So if it's the carrier must have the lowercase s. Okay, so the male will have two lowercase s's here. So when it comes to the cross, we'll do like how we did for the hemophilia. We'll follow the alphabetical order, yeah. H B A, H B S. The second one would be H B A, H B S. The third one would be H B lowercase s, H B lowercase s. The same goes here, H B lowercase s, H B lowercase s. Now, what are the genotypes? The only possible genotypes I have here is H B A, H B S, and also H B lowercase s, H B lowercase s. Okay, the phenotype would be I have carriers and I have afflicted. Okay, so the likelihood of a person having sickle cell anemia, okay, would be more prone towards the males. Okay, will be more prone towards the males because of the recessive gene. Okay, more prone to the male because of the recessive gene. Now, when it comes to genotype ratio, I only have two types of genes, so 1:1. After simplifying it, even the phenotype ratio is also 1:1. Okay, let's do another example. Same, I'll be using the same Punnett square, but this time I'll use a female which has sickle cell anemia and normal male. Okay, normal male. So once I start doing my Punnett square, I'll do the 2x2 square, and now I'll do the cross. Okay, now I'll do the cross. So HBA and HBS. Likewise here. Here as well, the third box. And the last one. Okay, so the female will be afflicted, which I put on the top part here, and the male I'll put on the left hand side. So from the genotype, the only two types of genes that I can get is not present here, but what I can see is all are the same kind of genotype, HBA and HBS. Okay, so if this is the genotype that I get, my phenotype should be all carriers. Okay, my genotype ratio is 1 and phenotype ratio is 1, because there's only single type of genotype and single type of phenotype. Now, when it comes to gender, then we have to do dihybrid crosses, which I will be using 4x4 square, but that is for another day. So guys, we have come to the end of the video. We'll continue in the next part of this video, where I will discuss past year question, analyze the question, and hopefully it will be beneficial to you. So thank you guys, hope to see you in the next video.